It's better. I mean, it's the same. Slightly better. Mic check. Okay. Yeah, I'm feeling a little bit sick, but let's do this. This one looks quite good. All right, day 5. I think it's about an hour long. So let's just Q&A. All right, here we go.
There we go. Okay, hello everyone. Welcome to Handmade Hero. This is day 5 of programming, and I was very excited to see everyone here. We have done a tremendous amount of work this week, actually. Despite only having an hour a night, we now have our very own animated graphics on the screen in Windows that we wrote entirely ourselves, which kind of opens the door for us doing absolutely anything we want to do. So, for those of you joining us who may be new, this is Handmade Hero. This is the the weeknight series. You can go to handmadehero.org and see. This is the weeknight series where we code a complete game from scratch, no libraries, no engine, just us, and we see how absolutely everything works, which has been a lot of fun, and I am looking forward to doing even more of it. So you can go up here on handmadehero.org to find more information about it if you would like to, and if you have questions or anything for me, there's an email a question button, and if you would like the source code, you can always pre-order the game, and it comes with the source code that we upload every night. All right, so let's get started. Today is a Friday, so we are going to be doing some recap about the things that happened this week. And basically, we spent the first day. Monday was not a very interesting day. We basically just set up our development environment. And Tuesday through Thursday, we got animated graphics on the screen, which was pretty cool. And so let's open up that file here. We basically put it all in one file. And one thing that I'd like to point out is there is not very much code here. It is really pretty straightforward, which I think is pretty great. Because one of the things that often intimidates people is they think that if they write everything from scratch, it's going to just be a huge amount of work. But it's not. There is very little code here, and we have done it in 3 nights with mostly me explaining things. So if you were to do this yourself, I think it would take you 10-20 minutes to put in some code like this. It is really not much code. What I'd like to do tonight is I'd like to kind of step through this and just really emphasize how every last little thing works so everyone can be on board with that. And maybe we'll try to start question and answers a little bit early if we do have time for that, so people can get drill downs into the things that they want. But before I get started, I wanted to clear up just a few things from emails during the week. So first of all, I wanted to thank I don't even know how to pronounce your name, I'm sorry. It's something like Kurt Karteltepe for writing in, because we did not need to order a capture card at the end of the day. It turned out that really all we needed to do was change OBS from monitor capture to the secret other monitor capture option. And I tested this, and it turns out that, yeah, if you switch it into this other mode where instead of capturing monitor, it's capturing a game, but you select the monitor as the game, suddenly everything works. And I didn't have any more problems like I was having, like the disaster that happened last stream. So thank you very much for solving that problem for us. That is way better than getting a capture card, because the capture cards was looking like they were a bit of a nightmare and had a bunch of drawbacks that I didn't want to deal with. So this is perfect. We are running smoothly, and I think everything will go well from now on, hopefully. Anyway, I also wanted to thank Martin Vladik for writing in. Again, don't know how to pronounce your name sometimes, because I wrote a thing here which was saying, let's check if HRedraw, VRedraw, and OwnDC still matter. And if you remember from the original part of the stream, we were filling out a win class structure here. And if you go back to the documentation and you look at the win class structure, although we deleted it because we were just seeing if it would do anything, in here you can see that there is a style field. And the style field, we had put some stuff in it. We had put in, oops, that's a lowercase style, not a capital. We had put this in there. And basically they were a bunch of styles. We ordered them together to set them all. And I was sort of hypothesizing, it's like, what exactly do we need these for? HRedraw is basically something that says redraw the window when you size it horizontally, and this is redraw the window when you size it vertically, and this is whether or not you have your own DC. We pretty much determined we don't need our own DC because it didn't really amount to anything that we would need to do. But it turns out that HRedraw and VRedraw are actually pretty good. Martin Vladik wrote in and tested them for us just to verify. But basically what it does is it's really just a flag that says I need to repaint the whole window when I resize it, not just the section that's new. So if I make the window a little bit bigger, instead of just painting the new section, I want you to have to repaint the whole thing. And what he pointed out was, he was like, well, if we're going to be stretching our image to fit the window or anything like that, we're going to have to redraw the whole thing, so we probably do want those in there, and he tested them to make sure they work. That was great work. Thank you for doing that exploration, and I think you are totally right on the money. So I'm going to consider that matter closed and say that we do want these two flags, so we are going to leave them in there. All right, that is it for my thank yous. Now I want to address just a quick little optimization thing. It may be a little bit early to talk about this, but I'm going to talk about it anyway. One of the things that I did when I wrote this function, Win32 update window, is I passed a pointer. So basically, we had a rectangle when we called Win32 update window. And if you go look at where we actually called that, you can see that I got the rectangle. It was on the stack here inside the WM Paint message, and I went ahead and passed a pointer to it. Now, the reason I passed a pointer to it was a bit of a habit. Usually I tend to pass pointers to things if the structures get large, and this is a 4-element structure, so maybe it's not that large, so it's a little bit weird that I did it, but, you know, force a habit, sometimes old habits die hard. And one of the things that someone pointed out when they wrote in, and it's a good point, is that typically one of the things that you want to try to avoid is passing pointers to things that are on the stack if you can avoid it, because the compiler now no longer really knows what's going on here. Because basically what happens is if the compiler sees something like this, where it's going to get the whole rectangle, the whole thing will be passed fresh to the function that is going to use it. There's a bunch of assumptions it can make. It can start to assume that nobody else is going to need to touch that thing. It can assume basically that it is just a private copy that this thing is going to use itself. There is no possibility for aliasing. There's no possibility for anything. What aliasing is basically something we'll get to a little bit later, and it's something you probably don't need to worry about too much right now. But basically it's just saying whether I have two pointers that might point to the same memory. And the reason that is important is because when the compiler is compiling your code, you can imagine if I have something like this where I've got two pointers, let's say, right, A and B. If I was, and these are pointing to something. This is pointing to memory. Both of these are pointing to somewhere in memory. And we don't actually know where they are, let's say, and neither does the compiler. They're just some pointers. Maybe they were passed into this function. We don't know where they came from. So if we have these pointers, and I'll take them out of the function just so we're not thinking about it in this const function. We're just saying somewhere in our code we end up with pointers A and B. Well, one of the things that can happen is I may want to write to A. I may want to go ahead and write something to A, right? And similarly, I may want to read something from B, right? I may say that, you know, I don't know, some other thing here, int x equals star B, or int y equals star B, right? Now, if you take a look at this code for a minute, it looks pretty obvious what's going on. I'm going to, oh, well, you know, I should probably even read out the values that they are, but point being, I can upcast an integer, that's fine too. Anyway, I'm going to read out of here 8 bits and shove it into these 32 bits of y. It's going to look at whatever is in the location pointed to by B, and it's going to put it in Y. And then I'm going to go ahead and I'm going to write 5 out, just the 8 bits that represent 5. I'm going to write those out to wherever A is pointing to. And then I'm going to reread B, right? Just going to reread the same thing. So at the end of this, we are all looking at it and we say, well, obviously, right, Y and X are the same, right? Because here is the pointer to B. We're reading it twice. It should be the same. So, duh, the compiler should just load it once, right? It should just turn that into this so it doesn't have to go out to memory 2 times to find out what that is. It should be efficient, right? Well, the answer is it cannot do that. And the reason it cannot do that is because we have not given the compiler enough information to know that A does not point to the same location as B. So it could be that this write to A right here, this write of 5, overwrote the previous value that was in star B, because if the pointer, I mean, if somewhere outside of here, before we got to here, if someone had done A equals B, well, then this code just reads and writes from the same location. So this will equal 5, right? But this will equal whatever was actually there before we wrote the 5. Right? Makes sense? Everyone on board with that, I hope?
Mm-hmm.
So that is called aliasing. It is a situation, well, it is one type of aliasing. There are actually a lot of types of aliasing, but that is pointer aliasing. That is what happens when you have 2 pointers that could point to the same thing, and the compiler does not know. So there are ways you can actually mark up your code to tell the compiler things about the fact that there is no aliasing and there's various stuff like this. But one of the easiest ways to do it is to just not use any pointers. So if you can get pointers out of the equation entirely, sometimes that's more effective. And one of the things that you'll note about this function is it is small. It is a very small function. It is a classic candidate for what's called inlining, which is where the compiler will go, hey, there is not much work being done here. Maybe instead of actually generating a whole function for it, I will just go to the place that it's called and I will just shove the code right actually in there. And if it's going to do that, that's pretty handy. It can go ahead and look at this and know that it's not, it can inline it and know that it's not actually a problem, to go ahead and assume that this client rec stuff is all the same. And you may be asking, and it's totally legitimate, Casey, if it's going to do that, if I just have a star here, why isn't the compiler smart enough to figure out that, hey, it's just a pointer, we're not changing the pointer, there aren't two pointers, what's going on, why do you think there's aliasing there? Well, the answer, and you should definitely defer to people who work on compilers for this sort of thing, the answer is that actually what the compiler ends up seeing at the end of the day isn't something quite this simple oftentimes. Oftentimes the optimizer happens at the end of a bunch of things that occur inside a compiler. It basically turns things into stuff like bytecode or pseudocode, different things called IRs, intermediate representations. The code goes through a bunch of transformations, comes out the other side, and then the optimizer gets this big, goopy mess. That is just the way compilers work. There's a number of reasons for it. You might argue it's a bad idea, or you may say that it's a good idea, but either way, that is what's going on in a lot of compilers. And so at the end of the day, this will probably not actually look so clean to the optimizer. It'll look like a bunch of different things. It'll actually look like 4 different memory locations, left, top, right, and bottom, that all came in here at the top of this code, and it has to sort of go back and do memory partitioning to go, oh, that's what's going on. There's a whole bunch of stuff that happens. So I don't want to belabor that point too much, largely because I am not an expert on optimizing compilers by any stretch of the imagination, and I am probably going to explain them poorly if I try to give you specifics. But point being, one thing you can do to help the compiler out is if you are passing relatively small things and you could pass them by value. Nowadays it is probably a good idea to do that, whereas in the old days it probably wasn't, because there wasn't as much compiler optimization stuff going on. Nowadays there is, so probably we should have just done that. Someone wrote in to suggest that we do that, and I think that's probably a good suggestion. I oftentimes pass things by value a lot of times, and that is probably a good one. So I say we go ahead and make that. But one thing that we could do in the future is we could look at the code to see what the difference was. In this case, it's not performance critical, so I don't think we really need to do that, but it's just something to consider. Okay, now that we've gotten rid of that, go ahead and do that. Now that we've gotten that out of the way, I have one more email that I thought was good to go over that someone sent in. Basically what they were asking, they were following along at home, which is awesome. The number of people following this series along at home has
all of it. I don't know if I was paying attention. Kind of. Okay, never mind. We'll just keep going.
Surprisingly large, and that is awesome. To all of you out there who are typing while I am typing, that is just totally cool, and I love all the stuff you guys have been trying and sending me questions. It's been awesome. Anyway, what they mentioned is they said, hey, when I was following along, I accidentally put this definition, the MSG, the message structure, I put it out here. Instead of putting it inside the actual run loop, I put it out here. And what he was asking is essentially, what is the difference? Like, what difference does it make to the actual code that gets generated where I put this? And again, that is an awesome thing to ask. That is exactly the kind of thing that I hope people are thinking about, because that is the kind of minutia that you want to learn, because once you learn it, you know it forever, and now you just have so much better idea of what kind of code is getting generated. And nowadays, people are very detached from the actual stuff the CPU is doing. And again, one of the things I really want to hammer home is it's great to stop that, to actually go and reach down and really figure out what's going on. It makes you such a much better programmer just to know. Anyway, the difference is essentially nothing. You will be heartened to know that most compilers, as far as I am aware, are pretty smart about how they lay out things on the stack. Now, basically what happens is when we come into this function, again, if you saw the intro to C stream, there is a stack, and the stack is basically something that is a block of memory that is reserved for our program as it runs, and it grows on the top and shrinks every time we call and return from a function. So we call into a function, it pushes onto this stack, it basically puts on the values that we pass to the function, and it puts on the values that that function needs for its local variables. So when we declare something like a local variable, like this win class here, like these integers, and like that message structure, it is basically just growing the stack out to make room to store that. So instead of actually doing an allocation, remember we did a virtual alloc up there to alloc a block of memory. Instead of doing an allocation, which is something that'll sit around for a while, it's just putting it on that stack. The stack kind of grows and shrinks, and it's just memory that ends up being reused. You can think of it almost, you know, like a watermark. You know, it's like we've got this pool. You know, we got this big old swimming pool, and it's empty when we start the program, and the water level rises, and the water level shrinks, and the water level rises again, and we're just using that big empty space. We're using the same space over and over again. So when you call into a function, it uses space on the stack to store the local variable, store the parameters that it uses, that sort of thing. When you return from that function, it backs up the stack to point, it no longer is using that area. But then the very next function you call will reuse that same area that was used by the previous function, right? So it's constantly getting reused, the stuff on the stack. So the question of what happens when I declare a new thing like this is basically that it's largely for your convenience where you put it. When you put something inside a while loop, what that means is nobody can reference it outside the while loop. So the reason that I put it there was because basically I didn't want people out here, I didn't want people maybe who were going to be, let's say someone right here, I didn't want them touching this. I didn't want them doing stuff to message in here. That's no good because message is only supposed to be something that's used as basically the only reason we have it in the first place is to get a result from peak message. So I certainly don't want them using it out there, and I definitely don't want them using it down here, which they could also do because it was declared up here. Remember, it is in this outer scope, this scope right here. So anyone in that block could use it. And so basically what I'm doing when I put things inside particular blocks and functions is really I'm just trying to make sure that they are sort of lexically scoped, meaning the people who can refer to them lexically scoped as narrowly as possible to avoid people accidentally referring to things that they should not be. And while it seems like that's an odd thing to protect against, it actually is kind of useful because oftentimes code gets moved around and cut and pasted in various ways inside a function, and you may accidentally leave something that kind of moves to some place it shouldn't, and now you've got a bug. So it's just helpful to kind of put that in there. It helps the compiler catch a few mistakes for you. No big deal. If not, a lot of people who program in straight C put all their variable declarations at the top because that, C does not have declare anywhere until C99. That's a habit some people got into, and so on and so forth, and that's totally fine. So you can certainly be a very productive programmer without doing that, but it's something to consider. So when you put it anywhere, doesn't matter where you put it, basically all that's going to happen is the compiler at its discretion at some point during the execution of this function, whether it's at the beginning or right when it sees it or any time like that, is going to enlarge the stack to hold it. That is the only real requirement, as far as I'm aware, that the compiler has to adhere to. It has to be able to do that, but it can do basically anything it wants to do to optimize it. So you don't have to put it out here to prevent it from basically growing and shrinking the stack all the time in here. An optimizing compiler, I should think, would be plenty smart enough to make sure that it can always just do that allocation, knowing that it's always going to have to happen, do that stack grow up at the top, and make it nice and efficient. So you can put it in there, and I don't think there's really any penalty. Now, it's worth noting that in C++, if you are going crazy with your C++ness, there is another thing to watch out for. And what that thing is that individual structures, classes, those sorts of things, they can have constructors and destructors. And what constructors and destructors are things that happen when something comes into existence.
Hey, Plusser. Excuse me, sorry. What's your Zig setup to Win32 API? I know I'm using Linux, so I'm not using Win32. I'm using X11. Should zoom it in. I know, that's fine. I mean, there's a lot in the title. So yeah, just using X11. I think it's the closest thing to Win32 in Linux. I tried the others, but this seemed to be the most similar. But my guess is you could just use Win32 here if you were on Windows. I think the only thing I had to do was, I think it was build. Yeah, just need to link it during build stage, and then it just works.
And when something goes out of existence, they're basically function calls that are triggered on those boundaries. And if you had something in here, like the message structure, if that had a constructor or a destructor, the definition of what the compiler has to do is it has to call the constructor when it is created, and it has to call the destructor when it is eliminated. So in that case, there would be something additional to think about. Putting it inside this while loop means that every time through the while loop, it would call the constructor right here, and it would call the destructor right here at the end of the scope. That is the compiler's responsibility. It does not have the flexibility to do anything else unless it can determine that it can safely defer that destruction in some way. It pretty much has to do it. That is the specification. And so there is a real difference, potentially even performance-wise, between that and this, if there was a constructor call, because that constructor call could be expensive, and the compiler is now doing something else in the loop. It is not just a case of it having to reserve space for this somewhere up here and just using it when it gets down here. It's not just lexical scoping. That is actually creating real program behavior. So that's something to be aware of. We will almost never be using anything like that in this stream, but a lot of programmers do use those sorts of things, so be aware of it. Okay, hopefully that answered that question pretty well, and we are done with the questions from the email. Now, one more thing for those of you who are following along in my .emacs file. If you look in my .emacs file in here, we've got .emacs in the MIST directory. I set my font to Liberation Mono. That is the font that I load. And it turns out that that is not a font that is often on machines by default. So if you would like to get it, if you're trying to follow along with my Emacs file directly, you want to type Liberation Mono into your Google search, and you can go on here to the Red Hat page and you can download it. That will prevent you from getting an error in the .emacs file. I would redistribute the font, but I don't know if that's technically allowed, and I want everything in this package to be distributable in the public domain, so I am not going to include it, but you can go get it yourself. Alrighty. All that said, that is the entire cleanup for the week that I can remember. So now is the time for us to kind of look at this code and go a little more in depth.
Zig always seemed intimidating with the syntax noise and the explicit allocator usage. I think, yeah, I mean, you're not wrong. There is a lot more syntax, because when I was trying to do the same thing that Casey's doing with C, there were a few things that just like pissed me off. But there was also me not knowing Zig very well, because I'm also quite new to Zig. I only started Zig 7 months ago, or maybe 8. I don't know. The allocator. There's one thing that I found really useful. If you go to the documentation, there's memory. Always just read this before I need to pick an allocator, and it's pretty good. They list like quite a few of the scenarios where you would need it. I can leave it in the chat if you want. I need to get my chat anyways. Check that. It's pretty good. Even if you don't use Zig, I think it's pretty helpful to know what kind of allocator to use. Or maybe not, if you don't use Zig, because I didn't see there's only one.
From what we were able to do when we were actually implementing it. So, first thing I want to do is I want to look at these global variables. These global variables are not something that I really like to have around.
Also, I'd like to say Plusser 27. I'm also quite new to the whole allocating memory thing. I've done C, but like long time ago. And I program mostly in Go now. So, but it wasn't as hard as I thought it was going to be. Most of the time you don't really have to think about memory that much. Yeah, most of the time. There were a few bugs that I created from me not understanding memory, but you figure that out quite early on.
Like I was saying, the reason for that is they kind of get a little, it gets a little confusing.
What do you program in quite, by the way? Goes quite nice. I've been writing my own Chatterino version in Go plus Wales. What's Wales? Okay. Cross-platform desktop apps. It's good to know. I've always wondered. Nice. Yeah, it goes pretty good. That's good. Yeah. It's like Tauri from. Yeah, I've heard of Tauri. But I think you have to write. The backend is in Rust, right? You can't choose the language. If I'm right.
To know who and when and where and.
But yeah, it goes pretty good. I like it. I use it for. I mean, I would say for almost most things.
So on, they are being accessed, and you can do that. You know, if you want to, you can work around that. Actually, if you have global variables and you like to use them, there are ways to work around that. You can do things like come in here. If you have a cleanly compiling program, you can add some random character to the end of a variable and hit compile again, and that will show you all of the places that it was used, because you will generate errors in all the functions that reference that. So that is one way you can figure that out. But I would rather go ahead and bundle these things up into something that's a little bit more concise. Again, this is not for performance or anything like that. This is strictly because I would like to keep the code in a way that's a little more clean, a way that's a little more manageable, so that we can see easily, no matter who is looking at the code, exactly what had to happen for these bitmaps, for this off-screen buffer that we created that we're drawing the screen every time to exist. And so basically what I'm going to do is I'm just going to open a struct, and I'm going to go ahead and put this stuff in there, all the stuff that we actually needed. So we knew we needed a bitmap info to describe our bitmap. We know we needed a pointer to the actual bits of that bitmap. We know that we needed the width and the height, and I'm going to go ahead and remove bitmap from these, because since they're in a structure now, we're going to know that. So I'm going to go ahead and remove bitmap from those. We're going to have the width and the height there, and we are also going to have the bytes per pixel. And one of the things that's nice about this, you can see we bundle this all up together, and now we know that anyone who needs to operate on this bitmap, we can just pass this structure, and we're going to call this our off-screen Win32 off-screen buffer for now, because I don't have a better idea for a name, so that's what we're going to use.
The memory footprint isn't that big for today's standards, I guess. The standalone Go app is about 15 MB RAM, and the WebView runtime is another 80 MB. Yeah, it's not bad at all. I guess the 80 MB is because it's run in JavaScript. Maybe. Yeah, I mean, yeah, that's much better than running Electron, I guess. So I'm actually quite curious now. Do you write the UI in JavaScript? Yeah, I mean, it's pretty. Okay, nice. I might check it out. Because I've used, what was the one? I think Raylib. And this is the one I've used in the past. And SDL3. But like, yeah, you got to build the UI yourself. Not as convenient. This one looks cool. I might check it out. Thanks for sharing that.
So basically, if I just bundle those things up, now anyone who has to use this can just get a pointer to one of these off-screen buffers, or pass a by value, as the case may be, and they're not going to modify it.
Do I have any globals? I think there's a few more things. Actually, I want to know how he handles the resizing.
And then they can go to town, and they know they have all the information they need, the width, the height, the bytes per pixel, and so on. So I'm going to go ahead and change our functions here to actually work on that. Now you can notice this render weird gradient. It will now take an off-screen buffer, and it knows to write to it. And you can see that we're kind of levering up. We've got a little bit more power here. The reason that we have a little bit more power is actually because now we could have multiple off-screen buffers. Before, when we had those global variables, well, if you did render weird gradient, it was always going to go into the same buffer, right? Same buffer. You could never have multiple buffers. But maybe we wanted multiple buffers for some reason. Who knows? Now we have the flexibility to do that because every time we call render weird gradient, we're going to pass it the buffer to use. And we could have tons of different buffers if we wanted to. So again, that's a lot of the reason for pulling things out of global variables, for pulling things together, is it makes it clearer and it also makes it more flexible. So the width and the height here, I'm just going to dereference into that buffer. And again, I don't know, this is a pretty giant guy. I don't actually know if I want to pass this guy by value. We could pass him by value because we're not really going to change him. So we could actually do it this way. And I don't know which one's better. You know what, let's do this. Let's actually go ahead and do that since tonight is an exploration stream. Let's see what the optimizer does. Let's actually take a look and see what the optimizer does if we pass this by value to see whether or not it does the right thing in either case. Okay, so I'm going to go ahead and pass that buffer in here, the buffer that's supposed to write to. And I will go ahead and change all of these things that have to happen. Bytes per pixel also coming out of the buffer now. The memory also coming out of the buffer. And that looks like just about everything. Let's see here. Yes, that is now clean. Looks like it's doing it. Now the pitch was computed. And this thing is operating off that. One thing that we could do here is decide that the pitch is also variable so we can have a little bit more flexibility with how we actually allocate that. So I'm going to go ahead and put that in there. And then I'm going to move the pitch computation down into here because we're going to need that in a second. All right. So here is our off-screen buffer. We're going to render our weird gradient to it. And it looks like that's pretty clean. Let me compile. That should compile that cleanly. Oops, nope. Got to get that out of the buffer as well. There's really no reason for me to dereference those buffer widths and heights here for referencing by value. We can just go ahead.
They're working on a V3 for the framework and claiming almost IPC memory sharing. I don't know what IPC is. Performance for transferring data from Go to JS. But they've been in dev alpha for a good while. On the V3, I'm guessing.
Do that, so that should be fine as well. And so that looks like a totally reasonable compile. Yes, so that is nice and clean now. Takes the Win32 off-screen buffer and draws to it. Now Win32 resize div section, that is going to take our Win32 off-screen buffer as well, but this is kind of interesting and something to note. What we have to do here, since we are changing this thing in place, we have two options, ladies and gentlemen, two options that we can do. If we were to pass this by value, that basically means that we have our own private copy of it, yes? It means that when this function is called, we are getting a copy of an entire buffer that someone else was doing, not the buffer memory.
Okay, because yeah, the thing, because okay, JS is calling into Go. Set up two processes to use the same page or memory. Not sure what the right terminology is, but if they can get close to that, it'd be crazy. Yeah, that would be wild. Yeah, it's quite interesting. I wonder how they even do that. Unless they have like a program then calls the Go and the JS processes individually. Okay, I can't get distracted.
Memory itself, because remember that is just a pointer that's inside here, and a pointer is just 32 or 64 bits, depending on how we're compiling. But we get a copy at least of this entire structure. So that means, excuse me, I'm still sick today. That means basically any changes that we make will not stick. So you notice we're changing a bunch of things. We're going to want to change a bunch of things in the buffer here. Right? We are writing to all sorts of things in this buffer. We are changing the width. We are changing the height. We are changing the bitmap info structure. We are changing the memory that it points to, and we are computing the pitch. We are doing all kinds of stuff, right? And since that is the case, that means that when this buffer comes into us and we get a copy, if we go change that copy, well, the person who called us is never going to see those changes. They're just going to disappear because this is a local variable that's on our stack now, basically. It's a parameter to us. So what we could do is we could, if we were in functional programming style, we could return, basically, a new buffer to them. So we could just return buffer here. So that's a local variable, and we could return it, and they would have to capture that return. That's a little bit error prone, so this is not a particularly performance sensitive function, so even if the compiler was going to have an easier time optimizing something like this, I don't think I would prefer that. What I would prefer is a situation where basically it gets a pointer to a buffer and just modifies that buffer in place. That is much more what I would prefer. Now really what we want to do is we wish Chandler Carruth was watching this stream and he could tell us if that was a terrible idea or not. We basically need some optimizing compiler author to come in here and tell us how bad it is that we're doing stuff like this. But at the end of the day, like I said, this function is called so infrequently that we really just don't have to think about the performance implications of this, because it is called once whenever you resize the window, and that is all. So it is not even called every frame of our game. It is not going to be on the critical path in any way. So I'm a little more comfortable writing it that way. I'm going to write it that way for now. But yes, if someday, for some reason, Chandler ever does watch this stream, please tell us if we are being stupid, because that would be...
Don't resize. Bitmap width. Where is that coming from? Oh, because it's global. Because it should be buffer dot something.
Excellent information to have. So I'm going to go ahead and change these dots to the arrow reference because we have a pointer to a buffer, not an actual buffer. So I'm going to do that. And the other thing that I will note is we actually store the width and height in here. So if we were being super conscious about space, we would get rid of these. I don't think that's necessary because, again, we've got so much memory to play with at this point, and that is a tiny little bit of that concern. So I'm going to go ahead and just finish up the porting here. We got to go ahead and free the memory out of that. We have to allocate the memory out of that. Yes, indeed. All of that is good. And we have, oh, right, we changed that just to info. So I'm going to go ahead and change, oh, you know what? Everyone loves this so much in the stream, I'm going to do it again. Kill rectangle. I do not know why they like that so much, ladies and gentlemen, but they do, so we need to do it. Cool. You have to give the people what they want. That's my opinion on that. Oops, got to actually change that to buffer as well. And here we go, buffer width. Buffer height. So again, I am doing absolutely nothing to the code right now. I'm just changing it to read out of that structure. And that is a little bit of an arduous process. I probably should have used a search and replace for this if I was smart. But what can you do? You think of things after they would have been good sometimes in programming. It happens. All right, so now we've got our resize set, and it will take a buffer to resize as well. And now we're going to go down here to Win3 update window, and that as well should now basically be, instead of update window, I think we're going to call that Win32 copy buffer to window, because that is what it is actually doing. Or maybe I will say display buffer in window, something like that. I don't know, whatever you like to call it. It is your code if you are typing in at home, and you have the control. You have all the control over what is going to go on. Do not let me brainwash you into typing in the names that I like. All right, so this guy, again, we're not going to change the buffer, so we could go ahead and pass by value there, so maybe we'll go ahead and do that. And let's go ahead and change the width and height to come out of the buffer. Let's change the memory and the info That looks good to me, and that should be everything except the calls themselves. Yes, it does look like that is the case. All right, so now we are not going to get rid of our global variables entirely just yet. Maybe we will later, but what I'm going to do is I am going to actually just declare now a global version of this thing, just to go ahead and quickly replace those places where we call it, and then we'll think about whether we want to replace it. We're going to call this the back buffer. The global back buffer for now, let's say, because we are only going to have one of them, so it doesn't seem like a particularly important thing to actually have that be local to anyone. Let's take a look here. Okay, I don't remember what order I even said that those things were in. Oops, didn't mean to actually create a new file there. Not my intention. Sometimes the Emacs keyboard shortcuts get away from you. It is totally true. All right, so this is the new function prototype that I made. We've got the device context. We've got the client rect. We have got the buffer now. This is global back buffer. We have got the parameters that used to be there, and that is everything. And the last one was render weird gradient. That just had to take the global back buffer as well. So let's take a look at that and just make sure that everything is copacetic with our code. Oops, changed the name of that. Display buffer window. Good to go. All right, so now here is the part where we see whether I was correct about the fact that the capture in OBS should be working correctly now. If I hit F5, let's see how we do. Oh, my goodness, that is not a good situation at all. Well, that is definitely good. This is our first access violation. One of the things I did when I pulled that off was obviously a complete mistake. Probably something that was pretty simple. But instead of going and fixing it right now, I just want to talk a little bit about what just happened. In fact, let's run the code again so you can see it. All right, so whenever, you remember when I talked about virtual memory, when I talked about virtual address spaces, I said that by default, we do not actually have any pages in our virtual memory space, reserved or committed. And so basically what happens is if we go touch some memory, if we have a pointer, basically, that we try to write to, and that pointer points to an invalid page, then we know that the operating system will basically get that exception. It will basically cause the CPU to go, hey, wait a minute, that page is not something I understand. It should not actually be touched by anyone. So it'll go ahead and raise a flag to the operating system. The operating system will go, oops, and it will say, hey, you are touching invalid memory. You are trying to write, in this case, write, it could be read as well. You are trying to write to a page that I have not actually put in physical memory and that I do not think is supposed to actually be ready for writing. Now, it could be, when those exceptions are raised, that they're totally normal. It could be, like, remember I was saying you can basically reserve memory and then it will only actually get committed to physical memory when you actually need to use it. So it could be that the operating system wakes up and goes, oh, he is supposed to be able to write to that memory, so I'm going to go ahead and actually back it into physical memory now, and that's going to be good. But that is not what happened in this case. So we got what's called segmentation fault on Linux sometimes, sig-seg-v you'll see sometimes. Signal segmentation violation, basically. Or on Windows, it's called an unhandled access, a UAE. I don't actually know what they call them sometimes in Windows. But anyway, it'll give you basically something that looks like this, where it says access violation, writing location, and then this is the pointer that you tried to write to. Now, if you notice, this pointer is awfully suspicious. It's all zeros. And basically what that means is we were trying to write to a pointer that we never initialized. So I probably just messed something up real quickly when I was changing the code to be using the buffer. And so we can go in and see. Now, it's pretty obvious what happened here. We're in the pixel. If the pixel pointer was 0, well, that means that our buffer pointer was probably 0, because there's no other way that could happen. So let's take a look and see. Yes, the memory is set to 000. So what happened there? Why did we not initialize that the way we thought that we did? So let's take a look. We come in here to Win32, resize div section. Here we are back out. This is in the WM slash call. It's passing a pointer to the global back buffer, which at this point should have absolutely nothing in it. It should be completely uninitialized. And it is. So let's go ahead and step into this code. We're going to virtual free, but we didn't have to because the memory was empty. We're going to set our header. That's all the stuff that we actually wanted to do. That's all perfectly good. We're going to try and allocate memory here. The bitmap memory size. Oh! Well, there it is, ladies and gentlemen. There is the problem right there. That bytes per pixel. Huh, awesome. Well, I hope you guys caught that. That was a pretty simple mistake. But just to be completely clear about what happens, remember I had bytes per pixel in here, and I moved it out, and I did not actually set it to anything. So that's our problem. We got to set bytes per pixel equals 4 there. This would probably be a good time too to talk a little bit about assertions. I'd wanted to put them off a little bit till later, but so I have not been putting them in the code at all. Assertions are things that probably would have caught that error for us. But at the end of the day, one of the things you have to remember is it's not that important to catch all errors. Basically, that is an error that will manifest itself very cleanly. If we have an allocation failure, we will immediately have an access violation. So those are not the kinds of errors that we really need to guard against that much. Basically, there's two kinds of errors. There are errors that are very insidious and difficult to find. There are errors that don't manifest themselves very often. And there are ones that'll happen every time you run the program. If you have an error that happens every time you run the program, that is not an error you have to be worried about at all. You do not have to worry about preventing that kind of an error because you will always find it before you ship. The kind of error that you do have to worry about is the kind of error that does not happen on every run through the program so that you may not find it until you ship, and that is bad news. And so this is probably not the kind that you should be too concerned about, but even so, that is the kind of thing that if I was putting assertions in this code, probably would have found it. And so that is something that we will probably cover. It is 8:30 right now, and there's more stuff I want to do, so we're going to leave assertions until about 2 or 3 weeks from now. So I will not quite do that yet. Point being, that was the problem. If you didn't catch it, what happened is we used to have bytes per pixel in here set to 4, and then I changed it to being in the buffer, but I neglected to initialize it to 4. That was just a stupid thing to do on my part. And so what ended up happening is when we went in here to compute the size of the bitmap, well, we multiplied the width times the height and got the number of pixels that we needed, and then we wanted to see how much memory we need for all those pixels. We multiplied it by 0. And guess what? You don't need any memory to store pixels that have no size. So it ended up generating a 0, which passed 0 to virtual alloc, and when you pass 0 to virtual alloc, it passes you 0 right back because, hey, it does not have to reserve any pages to store nothing. Not a surprise. So, we should be back in good working order unless I made another stupid mistake. Let's go ahead and double check that. Excuse me again, I apologize. Hopefully all my sore throat will be gone by next week. That is a much better looking size. We are in much better shape now. I think we should be good to go. So I'm going to go ahead and remove that breakpoint. And there is our beautiful pattern. Now you will notice how silky smooth that is tonight. Hopefully it's silky smooth on the stream. It's silky smooth for me. And again, that is thanks to Kurt. Thank you for writing in. We would have been in dire straits without you, my friend. Okay, so now that that is working, that is basically a very, very simple thing that you can do that I have shown, which is basically just taking something that was a bunch of global variables, pulling them into a structure, and now you have code that operates on that structure, which means you can have as many of those as you want to, and you also have a much easier time reading things because everything that you need is in one place. So that's always a good thing. Now, if we want to take this one step further, we could even get rid of this global variable. There really isn't much reason to do that because even though it makes it a little bit cleaner sometimes to do stuff like that, you don't want to go crazy and start doing things that you don't really need to do, because doing things that you makes the code cleaner in some conceptual sense but that don't actually have any real payoff for you is just making busy work. And that is a bad idea. There's a lot of that goes on in programming. A lot of people who do things because conceptually they believe something is cleaner, but really at the end of the day, it's just what produces good, bug-free code in the least possible amount of programmer time. That is what you're looking to do. Oh, and it should be performant, obviously. That goes without saying. So if you are doing something that is strictly for some kind of conceptual cleanliness, you are actually doing something wrong. Because if that cleanliness does not pay off for you, if it's purely conceptual and not practical, that is a waste of time. And time is of the essence, especially here on the stream, because we only get an hour a night, ladies and gentlemen. All right. Where to now? What?
Yeah, before it goes ahead. I guess I can do the same. Although, now that I think, my globals are all sort of mixed up. What do I call it? Back buffer, was it? Call it X11. Well, let's give it a width. $16. Can't be very big. $5, yeah. Hang on, what is the actual size. Resize. Configure, notify. Yeah, here. It's just an int. That means 32. I guess it doesn't matter. I'm thinking too much. Then for the heights. And what else do we need? Memory. It's a slice of bytes per pixel. Memory is just a slice of 32-bit. And what else? What does redraw need? Should I pass the arena as well? Why not? Standard dot heap dot arena. Okay, Thor. And I think display and window. Display is just a number. Display and window is pseudo window. Nah, I don't need the GC. How do I get the GC? Okay, maybe I'll add the GC too. Fair. Actually, hang on. I don't need this. Yeah. It's not going to be used after redraw. Okay. Global back buffer is Then I can get rid of these. Yep, there's a few errors, but I can fix that. Yep, I can get this bytes per pixel. And the memory. I guess if I pass the memory, I don't need the arena. Do all allocators have reset? T. Don't think so. Just leave it as arena for now. Right, and memory. Okay, yeah. Because I know the size. Right times. It's a lot of typing though. Can I just call it GB or something? Yeah, I think this one, I don't need to do this all the time. Or was it this one? Because it's going to be the same size. Resets the arena allocator and frees all allocated memory. Because I can reuse the same memory. think that's not necessary. Think so. Maybe. Not sure. Okay, I think that's everything. Today. Hang on, I got S Cloud. Zig. Can I reset a slice of V32? Okay, mem set. Sets all elements of memory region to element. Okay. This is called a memory. Take global back buffer. Can move this out of here. Can be there. Yeah, I'll just ignore the errors for now. Okay, and I think in redraw, no longer need that. What did I call the type? Back buffer. Oh yeah, I need to set buffer dot memory. So I guess pass pointer to 0. I'm not sure if this is necessary. To allocate X image. For the memory width. Okay, and then on resize. Resize buffer. What did I call it? Resize memory. Take that out and then pass it here. Arena is pointed to standard dot heap dot arena allocator. Okay, buffers resized. Bytes per pixel. 61. What am I passing it? Oh yeah, because it needs to be pointer. Where's resize? Oh geez. 18. Ximage does not support field access. Yeah. Why? Where's good image? Specify the width and height of the sub-image, which define the dimensions of the rectangle. Hmm. I mean, yeah, I don't think it's because it's a const. Does not support field access. Why not? The xCreate function allocates the memory needed for an Ximage structure for the specified display, but does not allocate space for the image itself. Rather, it initializes the structure byte order, bit order, and bitmap unit values from the display and turns a pointer to the Ximage structure. I mean, okay, I could just use buffer width and buffer height because they are the same. Yeah, that's not right. Should be global stack buffer. Okay, that's where we started. Resize, whoa. Resize is kinda janky, not gonna lie. I'd like to see how much memory it's using. I'm gonna ask Cloud. Can I see how much memory my Zig process is using? No, I don't want to do all of this. Yeah, I do have it. Where is it? No. Dot slash zig out. Binary. Handmade. Okay, I don't have it. How do you use htop? Doesn't work either. Okay. Can I specify real-time information about running process? Start. Seems like a lot of work. I'll just run and see what I see. That was the first command. Top. Well, I can see OBS. Say zig build run. Move it to the background. Okay, I see it here. Handmade. Go to that and get this out of the way. See if it changes drastically. Okay, that makes sense because it's double the size. and then it should stay the same. Yeah, and then if I make it smaller, okay, that seems reasonable. I mean, it's using a lot of CPU. That's fine. Well, what are these values? This is the virtual memory. What is the res and the sure? No idea. Okay, seems fine. Seems pretty stable. Because well, I mean, it would make sense if there was some animation, but it's constantly redrawing the screen. So all things considered, it's pretty good. CPU usage is quite high, but it's fine. Alright, that's good. Turn that back. Okay, I think we can continue.
What I would like to do, I think this program is relatively good so far. I don't have a lot of complaints about it, to be honest with you. But there's one more thing I wanted to pull out, and that is that we do this get client rect thing a lot. I was thinking maybe I would go in here and do something that basically made this a little bit easier for us. So I'm going to go ahead and make a little helper function. It's very simple. It is just going to be called Win32 window dimensions. That's all it's going to do. It's going to return a width and a height, just a very simple pair. And you will notice the reason that I'm doing that is you see this in a number of places. Get client rect, and then it has to do stuff with the width and the height, that sort of thing right there. So what I'd like to do is just get rid of that redundant code a little bit because it's kind of looking a little ugly and I don't love it. I don't love doing the same thing multiple times like that, so I am just going to make a very simple call just for my own sanity and convenience that is called get window dimension, and it'll take that window handle and give that back to us. So there it is. That is the entirety of what we actually wanted to do. So I'm just going to declare one of these. This is going to be the result, and it is just going to, instead of creating local variables width and height, it's going to write that result, and then it is going to return it. That is it. That is all I wanted to do. And so now I can go down to the places that we did get client rect. And instead of doing that, I can do Win32 window dimension. I can ask for the dimension, get window dimension, and I can pass that window. Now that will clean up nicely. And here we can just go ahead and pass those dimensions to our resize call. That looks good to me. We can come down here to the same thing that was happening and actually do the exact same thing. And I'm going to change this display buffer in window call because instead of taking a client rect, I would prefer that it actually took the window dimension because that is what it actually needed. So I'm going to actually pass the window width and the window height here so that it doesn't have to deal with those rect structures, and that makes that code go through the exact same path as the previous code, which is always good. It's always good to have the less code paths, the better if you can avoid having multiple ways of doing the same thing for no reason. It just means it's easier to change later and more likely to find bugs, because if there's bugs in each individual place that you do something, well, if you find and fix one, now you got to go and remember to find and fix all the others. All right, so what I basically did there is I said that when we were going to put it to the screen, instead of taking that client rect, it's going to take a window width and a window height. And you can see that all that had happened there is actually I had moved that window width and height computation that used to happen into here, so that's going to go away as well. So now we have it all done in exactly one place. That is pretty awesome. I love it when code comes together like that. You really can't argue with it. Of course, this is child's play with training wheels here. Obviously, we're just cleaning up some really simple code, so I wouldn't get too excited about it necessarily, but honestly, you know, what can I say? If it makes you happy, it makes you happy. You know what? I forgot to prefix that thing. Why do I keep hitting that hotkey? The code is getting generated. And
Press Control A by accident.
nowadays, people are very detached from the actual stuff the CPU is doing. And again, one of the things I really want to hammer home is it's great to stop that, to actually go. Sake. It is the goblin of small minds, they say. But you know what? Maybe our mind is small tonight. You know what? That could just be the case. All right. we are done with that. If I just can clean up the final... Oh, that's great, Casey. Nice. Gotta love the typos. Okay, and here we go. Dimension width and dimension dot height. Okay, now you may ask, while I'm cleaning that up, why do I keep passing dimension width and height instead of just passing the dimension?
Blah blah blah. I didn't know if you're gonna reply. Looks like you know your stuff. No, I really don't. I'm just winging it most of the time. I plan to make an FPGA project and try to implement RISC-V on it. I then want to run Linux. Okay. I don't know what FPGA is. I've heard of RISC-V. Then want to run Linux on it. Okay. I guess there's a question there somewhere. Get memory size. Which distro? What do you mean? Honestly, I have no idea. It's like I've never done anything remotely similar. I don't know, something like Alpine. I mean, yeah, I think the lightest one that I know of is Alpine, but I'm not sure if it's the lightest distro. Get Yeah, I mean, there you go. ABX. Well, ABX has replied. Seems like Tiny Core is the lightest. No worries, R. Good luck with your project. Unable to resolve com time value. Pointers. Cheers. How do you dereference? A reference. Okay, it's that way. Dot star. Okay, let's go. Still works. Yes, it does. I mean, it's a small method. Why comma? Guess it can't be outside of a method. Okay, that's fine. It's not the end of the world. Yeah, the rest is fine. What's this to do? Handle window destroyed or prematurely closed, so it can be restarted if it was unintended. Yeah, that's for later.
Mention itself. And the reason is because one thing that you want to make sure that you do is you don't go overboard with your type wrapping. So, the reason that I created that structure, the reason I created this structure right here is because I can't return two values from a C function. You can only return one. And so when I want to return two, I go ahead and make a structure that bundles those two together. That's why this is here. Otherwise, I just return two integers. And there's languages that support that kind of thing. And if you're using one of those, that is what you should do. There is no need to actually name this. It is not important. But when I actually start passing things, if I was to go down here and let's say change this to taking a dimension or change this to taking a dimension, what I have basically done is I have forced everyone who is ever going to call these functions in the future to bundle those things together again. They are now forced to create one of those structures in order to call my function, even if they already had the width and height from something else. And that is not something that I want to do, because basically when I make a function, I want the most number of people to be able to call it in the most number of circumstances, because that is what gives me leverage, and that is what allows me to reuse code the most often. So you don't want to get carried away with wrapping up your types. The only time you really want to force people to pass types to something is when those types literally have to all go together. Now, for example, in this off-screen buffer, that is a good making a good case for that, because all of these things are related. The pitch, the height, the width, the bytes per pixel, the memory, and the info all go together, and they cannot be used separately because they're all interdependent. Basically, this memory has to be a size that's dependent on the width and the pitch and the height and the bytes per pixel, and this info is set up to be specifically this layout. You cannot arbitrarily combine these things together. But Win32 window dimension is just an arbitrary width and a height that could have come from anywhere. It could have been from any window. You may have gotten it, not from calling this. And so I don't want to force people to pack things into some structure just to do it. So I didn't. Let's double check to make sure that we have not introduced any heinous errors by typos. We have not. That looks pretty good. Our resize is still working, so that's good as well. And that is all good. Now, I think that probably at this point, what I would like to do is go ahead and see, you know what, I might make one more thing before we drill down in the QA a little bit, because we've got about 17 minutes left. So there is one more thing that I think I'd like to try. Maybe this is a bad idea at this point in the stream, but I'm going to try it anyway. What I would like to do is I would like to start using our stretch split call to actually stretch our bitmap. I want to basically allocate this bitmap. Instead of allocating it in the WM size command, I'm going to stop doing that entirely. I'm just going to go ahead and say we're not doing that anymore. Instead, we are going to resize our bitmap right here. We're basically just going to go ahead and say that when we start up, we are going to make our bitmap a particular size. We are going to make our bitmap, let's say 1280 by 720. That is going to be the size of our back buffer. That is the way that I want that to work. And so now, when we go in and we do resize div section, we will do that just once. We will not do it on the WM size, and that back buffer will just sit around and get updated by us. Now, when we actually call Win30 display buffer in window, that will stretch it for us, because remember, we're passing the buffer width and height, which will now always be the same. They won't be changing, but we will be passing a different window width and a different window height. So if we go in here and run this, you will now see that basically as we stretch, oh, that does not look good at all. Well, when I said you will now see a bug is what you will see. So that means we are passing some incorrect things here. What did we do wrong? Oh, that's fantastic. I just assume I know what the bug is here, because I feel like we typed the wrong things in there. Even though we read the manual, ladies and gentlemen, we've read the manual, but we must have ignored it, because I am pretty sure those are in the wrong order. Let's take a look. It is the destination first. Well, guess what, people? That is not the destination. The buffer is our source. The window is the destination. Those are in the wrong order. That is no good. That has been a bug that's been lurking in there. Before, they were both the same, so it did not matter, and that is true. But now we have fixed it, and there we go. So there we are. We're stretching. And that's totally fine. That's what we wanted to have happen. But I would point out that that is not a particularly good stretch, ladies and gentlemen. That is not a fantastic stretch. It is certainly not doing a lot of filtering to help us out there. So that's something to be a little bit concerned about, something to think about. So we'll have to play with that a little bit. For the time being, though, that means we do have a back buffer that's sized the same, and that is something that I want to start out with. And we will have to think about how we're going to deal with some of those things, because stretch DI bits may not be enough. May not be industrial strength enough for us. But we'll think about that as we go. It's totally fine for now. So one other thing that's going to happen here is if we stretch in some kind of way that actually does something bad there, right? We're stretching like this, we're stretching like that. We end up basically distorting the aspect ratio of our image, right? We are drastically changing the aspect ratio. So if this was our little handmade hero, he would be squashed. He would be squashed horizontally, or he would be squashed vertically. So what I want to do here is I want to just take a second to go ahead and actually correct the aspect ratio when we do this split. Because I wanted to show you a little bit of math for that. It's very simple math, nothing really too much. So basically what we're going to do here is we're going to try and figure out basically how... All right, I got to think about this carefully. 15 minutes left. These are the kind of decisions that are hard to make. You know what? No, we're going to save the aspect ratio for later. The reason we're going to save the aspect ratio for later is because it's probably true that we will want to do this in floating point. Maybe not. Maybe we want to do it in integer. I don't know. It's such a tough decision. Sometimes the decisions I face on the stream, when the clock, it's the clock that makes the decisions difficult. I don't always know whether we should go for it or not. Well, the answer is no. We're not going to go for it. So I'm just going to drop a to-do in there. I'm going to say aspect ratio correction, and we will have a thing where we actually make sure we do that early in the stream so we can take the time to talk about how we're going to do it and do it 100% correctly. So for now, we're going to get a squash, and that is totally fine. But otherwise, we are totally good to go. All right. So last thing I wanted to do before the Q&A is we are going to go ahead and step through our code and make sure we understand what all of it does, so that everyone who followed us for this week can make sure that they really solidify their understanding of how the code goes. So let's go ahead down here and let's just set a breakpoint. Again, that's F9, ladies and gentlemen. Let's set a breakpoint right at the beginning. This is the first time that it enters our code. Now remember, we are not the first thing that happened. The C runtime library has already done a bunch of stuff, but there's not much we can do about that at the moment. There are ways to compile without it, but I don't know if we necessarily want to go there. We may try it at some point when we are feeling brave. Anyway, we go through here, and we are basically going to start by putting this window class, initializing it to 0. That, again, is going to initialize the window class to 0, basically because we have not put anything in the little brackets. That is the clue to the compiler to initialize it to 0. And where is that going to go? Well, where does any of this stuff go? All of this stuff goes on the stack. All this stuff goes on the stack. These parameters go on the stack. The window class went on the stack. And just to reinforce that, let's go ahead and take a look at that memory window, shall we? Here is the memory window. This is the memory in the computer. And actually, you know what I think I want that in a different place. I'm going to go ahead and just drag the memory window, and I'm going to go ahead and drag it down here so that it ends up down in here. That is not what I wanted. Ladies and gentlemen, I need to be a little more precise with my drop. There we go. Okay, that is the memory window. That is what I wanted. I'm going to go to the watch window, and I'm going to take the address of that window class. And so I can see where it is. So I'm going to take that address. There is the address right there. You can see it. It is a 64-bit address because we're in 64-bit mode, so we have big memory space. I'm going to go ahead and paste that in here and hit return. So this is where that window class is. You can see it. And it is not all zeros right now. It has got stuff in it, right? And I'm going to go ahead and hit F5 to step over, hit F10 to step over this line. And you can see that it all got cleared to 0 down there, right? So that is what's happening. This is the stack right here. And I just wanted to point out that if you look at where that is, 2CF5F0, right? 2CF5F0, where did you go? Right there. Let's take a look at those parameters. Instance, prev instance, and command line, just so we can see where they live as well. There you go. You can see that they are all right next to each other, which is what we would have expected because it looks like the compiler has pushed them onto the stack. It pushed them on the stack sequentially. We can see what order it put them on in the stack as well, right? You can see they go in order here, 30, 38, 40, and 48. And if we go ahead and look at where that is, we can see they are at 2CF7. They are a little bit further down. I will widen this out. So basically here is the one that we were talking about before, 5F0. It is right there. That is that one. And the 7s were over here, if I remember correctly. Yes, they were. Okay, and so what that leads me to believe, although I do not actually know, that would suggest that it is pushing these, that the stack is growing downwards. I don't actually know if that's true. That may not be true. It seems odd that it would push them in that order, so I'm not sure what order this stack is growing in. So let's go ahead and see if we can figure that out. Let's jump up the call stack one. I just want to know whether the stack's going up or down because honestly, it's been so long since I've looked at anything like that. I have no idea on x64, which is what we're doing now. I have no idea if the stack gets bigger off the bottom of the stack or off the top of the stack. Let's find out. All right, so see, here's a variable, init_ret. Let's see where that is. Oh, it was optimized away. All right, well, all right, so much for that. Let's call into one of our functions then and see where it is. So let's go down here real quick. Actually, you know what? No, we can do, why did I do that? We can actually do that right here now that we're allocating our back buffer. All right, let's take a look. Window class. That is where window class was placed on the stack. That is this location in memory, 1FFCA0. And all I want to know is whether the stack grows downward or upward, meaning when you push new things on the stack, do they go at higher addresses or do they go at lower addresses? That's all I wanted to know. Just wanted to get that out in the open. So let's take a look at where some of this stuff goes. So here we are, bitmap memory size. That is a local variable. It should be on the stack here. Let's see where it is. And so 1FFCA0, and we have 1FF BF0. That looks a lot to me like we are growing downwards, ladies and gentlemen. Let's just verify that that's true. That does not necessarily surprise me, but I just want to make sure that that is true. Oops, that is the wrong way to go. So this is the value that is lower. This is the one that's further down in the function, basically in the depth of the function. This was the one, bitmap memory size. And so this was a function that we called the deepest nested function. And here's the one from the function that called it. Hit return, it is 176. Yes, so our stack is growing downwards. What that means is that every time something new is pushed on the stack, it goes at lower and lower memory addresses, which is a little odd because normally you think of things as growing and getting higher and higher, but it looks like the stack is growing downwards. Just something that's good to know. Does not really affect anything in any particular way, but just something interesting to think about. Also, I guess that means, and those of you who are hardcore assembly guys, correct me if I'm wrong on this. I don't want to speak out of turn, but I guess that means that if this is the value that the stack is at now, that's the entirety of the stack size we actually get. So basically, we can only add about 2 megabytes to the stack before we would get to the null page at best. So it can't be any more than that. Our stack must be less than 2 megabytes. I don't
I'm going to call it today there because I actually watched the rest of it accidentally. Plus I'm a bit sick too. Right, I think that was quite nice. It was nice and easy. before. Oh yeah, I'm now looking forward to the next one. Keyboard input and sound. Either ways, I think we'll figure it out tomorrow. Alright, I guess thank you for hanging out. Hope you have a good day, whatever's left of it. And I shall see you back here tomorrow. Oh jeez, these guys are like relentless. They never stop. It's like, how many times do I have to ban you? Alright, never mind. Have a good one.